think we will all like this problem. I'm mainly going to talk about letter C, but I'll mention the other ones as well. But real quick with the other ones there, part A just says take the derivative. So simply multiply by the power, decrease the power by 1. Remember to times it by the derivative of the inside, 2's cancel, and then just get rid of your negative exponents. Boom, letter A is done. Letter B says write the equation of the tangent line, gives us a point. Now to get your point, it gives you the x value, right? So you know to get the y value, you got to take that -3, plug it into the original function to obtain that y value. So that's what I'm doing right here to get my point. Plug that -3 to the original function, got a y value of 4. So there's our point. And then you know the derivative is your slope. So to get the slope of the tangent line, you take the -3, plug it in for x into the derivative. So that negative is there. When I plugged in the -3, the two negatives cancel out, give me a +3, and then you just get the 25 minus 9 in there. So the square root of 16 is going to give us 4. And then once you get your slope as 3/4 and you got your point, if you have a point in the slope, just do your point slope form, get the equation of the tangent line. So A and B be pretty good. You guys did a lot harder derivatives than that. You did the equation of the tangent lines, pretty much every single section there. So we're going to be good there. And then before I talk about letter C, letter D, simple u du, right? So let your u equal the inside of the radical, do your du, balance the -2 with the -1/2, integrate that, go u to the 3/2 divided by 3/2, which means you times by the reciprocal. And then you got two options here. You could either stop and switch your x's to u's, or you can plug your x's back in. So if you plug your x's back in, you get to use the original numbers, the 0 and the 5. So you plug in the 5, you plug in the 0. Or if you just stop right here and switch your x's to u's, if I take the 5 and plug it in, 25 minus 25 gives me 0. If I take the 0 and plug it in, I'll get 25 for that. And I'll plug in 0 for the u, plug in 25 for the u. And then this is a no calculator problem. So I always pull out those extra constants in front so I don't have to worry about them. And when you're doing this, if the no calculator, I ain't trying to do 25 cubed and then do the square root of that large number. I'm going to always do the bottom one first. That's your root. So you do the square root of 25, which is 5, and then 5 cubed will get you that 125. Negative carries down, negative times negative. Boom, that's going to be a positive right there. So we like that problem. Derivative, tangent lines, integrals. What I want us to focus in on, we can get those right just because, right? Because we're smart and we're good at this stuff. Letter C, I would like us to study this a little bit. This definition of continuity. For a while, this disappeared, and then it popped up quite frequently the last several years. When you do the formal definition, kind of here's what you're gonna do, right? If I give you a piecewise and say, is it continuous? This is a line that's continuous ever by itself, okay? F of x is going to be continuous in between -5 and a +5, and that's where this problem is existing, all right? You can use any number in between 5 and +5, and you're going to get an answer for that. So the only possible point of discontinuity is where the pieces connect, right? Sometimes they might connect kind of, and together at the same y value, or they might connect, one might have a y value of 2, one might have jump up to a y value of 4, and they might not, there might be a jump in your graph right there, right? So what we always did in the past is we would just take the cutoff number like -3 and plug it into both the top and the bottom function. If we got the same thing, we said that was continuous, right? But if they specifically mention, hey, use your definition of continuity, you can't exactly do just that, right? That's really what you are doing. All I want you to do though is plug in the limit notation with there, okay? So on your blue packet, the second page where it says the common theorems and definitions, you have your formal definition of continuity. We did this in chapter 1. Continuity at a point, you have to have a y value, so f of c is defined, and then the limit as x approaches the exists, okay? So and it's a finite, it exists, and it's a finite number. And then the limit has to equal the y value. So you have to have a limit, you have to have a y value, and they have to be equal to each other. So what I want you to do on these is plug it into both of them, see if you get the same thing, but then you have to write it down with this limit notation. So first thing, to show that the y value exists, g of negative, so it says at -3. So I'm gonna find g of -3. So g of -3, that's where the bar's at. That's this guy right here. That's equal to f of -3. And we already said when I plugged in -3 for that x right there, it did give me 4. So that's the first part of that formal definition of continuity that says f of c is defined. So that means g of -3 that actually exists. And then when you're plugging it into the top function and the bottom function, just squeeze this limit notation in, right? So when I do the limit as x approaches -3 from the left and a limit as x approaches -3 from the right, when you come from the left-hand side, that's like your -3.001, right? That's going to be over here where you're plugging into that top function. So all you're doing when I'm doing this limit is I'm really just taking -3, plugging in right there. So this guy is equal to f of -3, which we set up there, that was equal to the 4 for the same reason. This one here, when you say limit x approaches -3 from the right, that's like -2.999 side. So that's from this side over here. That's using your bottom function. So you're going to take -3, plug it in for that x. So you're going to go -3 plus 7, plugging it into that bottom function, and you're also getting 4. Now, since you got 4 for both of those limits, that means that limit exists. So that's the second stipulation for your formal definition of continuity. And then once you have a y value existing and that limit existing, since they're equal to the same thing, I can say the limit is equal to that y value. And so since that limit is equal to the y value, that's proving that the g is continuous by your formal definition of continuity. So we could all just plug it into the top and bottom function and see if we're getting the same thing. Now, if I did get two different things for the top and the bottom, then I would have said limit doesn't exist. Left hand is not equal to the right hand, and I would say G is not continuous because that limit doesn't exist, right? So wouldn't hurt to just study that kind of problem and make sure you know your definition of continuity, because that could be something across the nation that others are weak on. So and that's something that you haven't done every single day, like the other parts of that problem. So please study that and just practice that on your own from scratch there. Fruit cup.